This is chapter 4, section 2, number 63. They're asking for regions of concave up, regions of concave down, and any possible inflection points that we might have. So how do we do that? First, you have to know what separates regions of concavity, and all of you should immediately say where the second derivative is 0 or where the second derivative does not exist. So very similar. If you understand the first derivative, that gives you regions of increasing and decreasing and relative max mins. The exact same thing with the second derivative gives you regions of concave up, concave down, and inflection points. So they're highly related. If you understood increasing, decreasing, rel min, rel max, it's the exact same thing for concave up, concave down, inflection points, but easier in just using the second derivative instead of the first. So if you understood the first, you should understand the second. Okay, so we need to find the second derivative to find regions of concave up and concave down. So I will do that. Now, if it were ln of x, it'd be 1 over x and we'd be done. And that's a t, by the way. So I need to make this t. So we're doing g prime of t. But it's not ln of t. It's ln of a function. So it's going to be chain rule. So what's ln of box? It's 1 over box times the derivative of box, which is 6t. Okay? Let's rewrite that like this. Now to find the second derivative, we're going to have to do the quotient rule. Le quotient rule. Un momento as I check something here. All right, so the quotient rule. We're going to do low d high minus high d low over low squared. So low d high minus high d low all over low squared. Wow, did I do that right? That looks weird. Let's try it again. Low d high minus high d low. Oh, I guess that's right. So what are we going to do? We're going to simplify the top, distribute the 6. We get 18t squared plus 6 and multiply. This is 36t squared. And let's combine like terms. The bottom is going to be 3t squared plus 1 squared. So 18 minus 36, that's going to be minus 18t squared. I hope I'm doing that right. So that's my second derivative. So what do I do with that? Where can my function change from concave up to concave down and vice versa? Where the second derivative is 0 or does not exist. Okay? So I'm going to set the numerator equal to 0. That's when it equals 0. I'm going to subtract 6 for both sides. Divide both sides by negative 18. Square root both sides. Do not forget the plus or minus. And I'm going to rewrite this as plus or minus 1 over radical 3. So those are the two places where my concavity could change and I could have an inflection point. Okay? So let's do this. What number are we doing? 63? Okay, looking good, looking good. So how do I do that? You don't have to do it with a table, but I highly recommend you do a table. The top of my table is a number line. I'm going to have my 2 critical points. No, they're not critical points. Liar, liar, pants fire. Critical points when the first derivative is 0 undefined. This is where the second derivative is 0 undefined, so it's not a critical point, but it's a point where I have a potential inflection point. A number in between that's pretty easy. Now this is bigger than 1. So 1 divided by bigger than 1 is smaller than 1. So I know -1 and +1 are outside those bounds. Okay? So we have that. Let's look at the original function to see, do we have limitations on what t can be? Okay. For an ln function, just to remind you, I can only take the ln of numbers greater than 0. ln doesn't exist at 0 and doesn't exist for negative numbers. So are there any values of t that will make this negative or 0? And the answer is no, because if I put a 0 here, I get 1. Any other number here squared is positive. A positive plus 1 is always positive. So the domain are all real numbers. So my left bound and my right bound will be -infinity, infinity. So you should see this as a number line going from -infinity to infinity with 2 points posted. This is 1 point between. 3 regions have been created. So this is going to be my time t, and this is going to be my second derivative of g. And again, if you're memorizing all that and you're not sure why you're putting it there, you're not doing yourself a favor. Why do you have the second derivative here? Because the second derivative tells us concavity, and that's what we're looking for. So it only makes sense to have the second derivative. Why are those numbers there? Because where the second derivative is 0 or undefined, those are the only places where it can change signs, the second derivative. So what this means, everywhere from -infinity to -1/3, the second derivative is either always positive or always negative, does not change signs. So I can pick any number, -1, -2, -100, -1000. They will all give me the same sign for the second derivative. Same thing for between these two. I can pick any number between, and it'll always get me the same sign, either positive or negative, and same thing for that region. So you can pick any number in those regions and it will work. All right, let's put in 0. I like 0 because 0 is easy. If I put a 0 there, 6 minus 0, that's positive. And the bottom's always positive because it's squared. The bottom's always positive. Positive divided by positive is positive. So I know the second derivative is always positive in this region, and we'll talk about that, the implications of that. Let's plug in 1. Put a 1 there. 6 minus 18 is -12, so it's negative on top. This is always positive. So negative and a positive get me a negative. So everywhere to the right of 1/3, the second derivative will always be negative. Then I'm going to plug in -1. -1 squared will give me 1. That's going to be -12 on top. The bottom's always positive. That's always negative. So from this, I'm pretty much done. I'm going to come to my conclusion. They want to know when it's concave up, when it's concave down. I will say G is concave up where? On one interval. On the interval from -1/3 to 1/3. Why? Because when the second derivative is positive, my graph is concave up. That's something you should know for any quiz coming up in your near future, hint, hint. So therefore, G is concave up on the interval. Why? Because G double prime, I'm going to write the words out, is positive on that very interval. Okay, where is it concave down? G is concave down where? On 2 intervals. -infinity all the way up to -1/3 and 1/3 to infinity. Okay, again, that region and that region. So those are these 2 regions. Why? Because you're allowed to put a B/C for because. I'm just showing you different notations. I'm not being consistent. Because G double prime is negative. Instead of saying is negative, I'm just say less than 0. just to show you some variations of what you can write on those intervals. On those intervals. Okay, I've done concave up, I've done concave down. They ask for inflection points. You need to know the justification for an inflection point. An inflection point justification is if the second derivative changes signs. Does it? Yeah. Right here, it went from negative to positive, and right here, it went from positive to negative. So I have inflection points at those 2 points. So I would say G has inflection points. Whoopsies. Kind of got sloppy there. At x equals plus or minus 1 over radical 3. Why? Because G double prime does what? Changes signs at those, wow, my writing is getting sloppier and sloppier, points. Done. So you've shown concave up, concave down regions, and inflection points.